We have of circuit analysis and design. Here we have presented our RL circuit. Now we will solve that such that we will draw its Norton equivalent. You already know that from previous course what is Norton equivalent and what is Thevenin equivalent. For RC circuits, you will draw Thevenin equivalent, but for the inductor circuit, you will draw Norton equivalent. So here you can see that this is a box in which we have some resistors and sources. So we will make a current carrying source independent. Now here we have a resistor that will be called as an Norton equivalent resistance. And now this is the part. This is exactly that was cut from here. Now you have an inductor. So presented by L, the voltage across this inductor is presented by VT. Let me write with another pencil. And now this is the voltage called as VT. This is the current that is passing through the inductor. We presented by I of t. This one is Norton current, presented by I of n. And again, this is a function of time. So this is Rn. Now, we will solve this circuit. How we'll solve that? We will write all the current. So we have In of t is equals to that current passing through resistor, that is I of R plus It. As we don't know the value of I of R, so we'll write it as Vt by Rn plus I of t is equals to Norton equivalent current, that is a function of time. As we know that terminal voltage across the inductor, that is Vt, and this is equals to Vt is equals to L di by dt. So our equation becomes L di by dt divided by Norton equivalent plus I of t equals to I Norton, that is a function of time. So this is basically a generic form of differential equation that we will solve in future. But now again, we will solve our circuit for natural response. And you already know what is the natural response when there is no source connected in the circuit. So we have a resistor and we have an inductor. So this one is L, the current passing through inductor, we will write it as I of t, and the current that is passing through resistor, that is presented by I of R, and the voltage across these 2 points is Vt. So again, we are going to write the equation. So IR plus I of t is equals to 0. So we will write as IR as V over R plus I of t is equals to 0. So again, VL is equals to L di by dt divided by R plus I of t is equals to 0. Again, differential I is also a function of time. As we have solved already previously in our last lecture, we see that this is equals to I of t, this is equals to I naught e raised to power minus t over L over R. As you know that this is L over R. Previously it was equals to RC. So this L over R can also be written as I naught e raised to power minus t over tau, and tau is equals to L over R. And for RC circuits, this is equals to tau was equals to RC. Now these are the things we have to keep in our mind. Again, the graph will be the same as the previous one, but now we will solve some of the examples. How to calculate the time constant. Here we have a circuit. This is a solid example of our book. So we have a resistor, we have an inductor, and we have some 2 resistors that are in parallel. So overall, there are 3 resistors. One is R1, one is R2, this one is R3, and this one is inductor. Now we want to find out the time constant. So first of all, we need, and you know that what is the value of time constant, and that is equal to L over R equivalent, and L is also equivalent. Here we have only one inductor, and there are 3 resistors. So what we will do, we will cut our circuit from these 2 points. So any resistors that come in series and parallel. So we have, let's redraw for, this is R3, this is our 2 points, this is R1, and this is R2. So you can see here, your R1 is parallel to R2, and that is in series with R3. So our R equivalent will becomes equal to R1, R2 over R1 plus R2 plus R3. So our total torque, it's not torque, it's tau, time constant, that will becomes L over R1, R2. Let me write here. So tau will becomes L over R1, R2 divided by R1 plus R2 plus R3. This is the total time constant. Now we have another example. Let's solve it. They're very quite simple examples. So we have example number 2. Again, we'll draw some circuits. Here we have 2 capacitors. One is C1 and the other one is C2. And we have 3 resistors that are in parallel. We will write these one as R1, this is R2, this is R3. And we will join these 2. So you know that how to calculate the tau. This is equals to R equivalent and C equivalent. So first of all, we will find out C equivalent from these 2 points. So our C equivalent will be equals to, as we have 2 capacitors that are in series, but we will find out its parallel equivalent just as we find a parallel equivalent of resistors. So C equivalent for this one will be equals to C1, C2 over C1 plus C2. This is very easy. When I'll tell you the resistor value, then I'll tell you a shortcut. So to find out the value of R equivalent, all 3 resistors are in parallel. So R equivalent is equals to R1 parallel with R2 parallel with R3. So if you guys have calculator, so it's very easy to calculate the values of when they are parallel. So what you do, you get R1 inverse plus R2 inverse plus R3 inverse and whole inverse. So if you have 4 resistors, 5 resistors, 10 resistors, or even if you have 100 resistors, you will find out the inverse of each individual one and add them all and find out the inverse of it. So this step is a single line if you have a calculator in front of you. But we are not doing with the numerical values. So we will write it as what is the value of R equivalent. So this will be R1, R2, R3 over R1, R2 plus R2, R3 plus R3, R1. This one is very easy. So our total time constant, that becomes C1, C2 over C1 plus C2 multiplied by R1, R2 and R3 all divided by R1, R2 plus R2, R3 plus R3 and R1. This is our answer, and this is how we will solve our future numericals. As we will move on, you will understand better. Thank you very much.